Alright, how are you guys doing? Good, I hope? Today we're doing it. We're expanding our list. We're jamming on music and expanding our list of famous tests to determine whether a series converges or diverges. Today we're looking at the famous alternating series, which will involve a test of some sort that will help us figure out a big family of these. So consider the famous series. This one is called the harmonic series, famously divergent. If you add all these up, infinite many of them, you get infinity. The question is, what would happen if you were to not add so many of them? In other words, what would happen if you were to, say, maybe subtract some of these and add some of those and subtract some of the other ones? What would happen if you alternated the signs here? Of course, some of the positiveness would be subtracted by some of the negativeness in some of these terms, and so you may wonder, well, maybe you don't get quite as much as you do with just having them all positive, which would be infinity. That's exactly what we're studying today. So if you consider the alternating sum, that would be this one. They're characterized a lot of times by this -1 to the n. That forces for even numbers to give you a positive term. For the odd ones, it gives you a negative term. And so you get the alternatingness from it. According to the alternating series test, under some good conditions, all you do is check the conditions and boom, you're done, just like that. So the conditions go something like this. Suppose the sequence is actually alternating, meaning this means that it should have alternating signs. One of them is positive, the other one is negative, the other one is positive, etc. It doesn't matter which one you start off with, as long as the signs of each of the terms is really alternating. That's the first condition. In addition to that, suppose that if you just ignore the signs for a second, if you just focus on the absolute value, the magnitude of each of these numbers, that should be decreasing and ultimately going to 0. So if you check these three conditions, every time you're able to carefully check this condition, the signs are changing, check this condition, the sequence is decreasing, and check this condition, it's going to 0. If you check those conditions, you're done. You can conclude safely that the series converges. So for example, let's take a look at this one. It's easy. You just first thing we do is we check, is it alternating? Well, yeah, because if you plug in n is equal to 1, you get -1 over 1, and then you get, for 2 you get 1 over 2, for 3 you get -1 over 3, etc. So for sure it's alternating. Is it decreasing? When I look at the absolute value, well, take a look at the absolute value of an would be equal to the absolute value of -1 to the n over n. I'm just plugging things from there. That absolute value would kill any fluctuating sign on the numerator, so it would just give you 1 over n. And in fact, this is clearly decreasing because as the n's get large, the denominator gets large, so the quotient gets smaller, making it decrease. And clearly the absolute value of n, which is equal to 1 over n in this case, clearly the limit as n goes towards infinity goes to 0. So we have the three key ingredients. Every time you can check these three key ingredients, the party's over, you're done, and you can conclude that that series converges by the alternating series test. Okay, so in this case, check that, it's alternating, goes to 0, boom, you're done. Okay, just like that. Check these three items. Okay, that was easy, right? Okay, let's take a look at another example.